Welcome to UGC lecture series Linear Integrated Circuits. In this lecture, these are the topics we are going to discuss: the design of Schmitt trigger, a stable multivibrator, working principle of a stable multivibrator, derivation of the frequency of the output waveform, and design of a stable multivibrator. In the last lecture, we have seen the working principle of the Schmitt trigger, which is otherwise known as a regenerative comparator. A positive feedback is given to the comparator, and so it is a regenerative comparator since the output is regenerated again and again because of the positive feedback. The design of Schmitt trigger: in the Schmitt trigger circuit, R2 is given as 100 ohms, R1 is 50 kilo ohms, V reference is 0, and the input voltage is 1 volt peak to peak sine wave, and the saturation voltage is plus or minus 14 volts. Determine the threshold voltages. We have derived the threshold voltage, say the upper threshold voltage, as we have derived with the superposition theorem, one with the reference voltage and the other with the saturation voltage, that is the output of the comparator, and now the reference voltage is given as 0. So, with only the saturation voltage, if the reference upper threshold voltage is given calculated, then the voltage, the upper threshold voltage will be V saturation into R2 divided by R1 plus R2, and here R2 is given as 100 ohms and V saturation is plus or minus 14 volts. Since we are calculating the upper threshold voltage, we have to take this as 14 plus 14 volt, and R2 is 100 ohms divided by R1 plus R2. R1 is 50 kilo ohms, so 50,000 ohms plus R2 is 100 ohms. So, it is 14 into 100 divided by 50,100. Some maybe the volts in millivolts range, and you can calculate it using the calculator. Now, for VLT, it is just the reverse of the saturation voltage, that is minus 14 into 100 divided by the same 50,100. So, these are the threshold voltages. You can calculate it later. If the reference voltage is 0, then the threshold voltage is simply written as V saturation or plus or minus V saturation R2 by R1 plus R2. These are the R2 by R1 plus R2 is called as feedback factor. Beta is equal to R2 by R1 plus R2, feedback factor. So, this is the simple design of a Schmitt trigger when the resistors R2 and R1 is given and V reference is 0. With 1 volt peak to peak, this is not at all used in this calculation of the threshold voltages, and the saturation voltage is given as plus or minus 14 volts. So, this is the formula to calculate the threshold voltages if the V reference is equal to 0. And next is, the next topic is a stable multivibrator using operational amplifier. It is a free running oscillator, you can call it as free running oscillator, and the circuit generates a rectangular output waveform using an RC timing network and voltage divider network. The RC network is connected to the inverting input of the operational amplifier, and voltage divider network is connected to the non-inverting input terminal of the operational amplifier. So, this is the RC network which is connected to the inverting terminal, and this voltage divider network is connected to the positive terminal of the operational amplifier. See, there is no input signal given externally to any of the input terminals of operational amplifier. In this astable multivibrator, the output has two states, neither of which are stable, and it is constantly switching between these two states, with the time spent in each state controlled by charging and discharging of the capacitor through the resistor. When you look at the circuit of a stable multivibrator, the RC network is connected to negative terminal. This capacitor is charging and discharging towards the output of the operational amplifier through the resistor R1. This capacitor will charge and discharge to the voltage at the output of the comparator through the resistor R1, and the positive terminal has the voltage at this point. This is the voltage which is fed back to the positive terminal of the operational amplifier, and here there are the output is fed back to the negative terminal as well as to the positive terminal. There is no external signal given to any of the two inputs of the operational amplifier, and the voltage present at these positive and negative terminals are going to be compared, and according to the principle of the comparator, the output is going to get transition from plus or minus V saturation. Now, if the voltage at the negative terminal is higher, then the output have negative V saturation. If the voltage at positive terminal is higher, then the output has plus V saturation. This is the function of the comparator. And now say for example, if the output of the op amp is plus V saturation, then the voltage at the positive terminal, say through this potential divider, it is divided and it is fed back to the positive terminal, say it is beta V saturation when the output is V saturation, plus V saturation, and beta is the feedback factor which is equal to R3 divided by the total resistance R2 plus R3. So, when the output is plus V saturation, the positive terminal has beta V saturation, and the capacitor is charging towards this positive V saturation through the resistor R1, and while charging, when the voltage across the capacitor is just beyond this voltage, that is just above the beta V saturation, then this voltage is higher than the voltage at the positive terminal. So, the voltage at the negative terminal is higher, then output will get transited to negative V saturation. The output will be now the minus V saturation. And what is the voltage at the positive terminal now? It is minus beta V saturation. And what happens to the capacitor? Now it is discharging towards the output voltage minus V saturation through the resistor R1. While discharging, when the voltage across the capacitor is just less than the voltage at the positive terminal, or the voltage across the capacitor is just less than minus beta V saturation, then at that point this minus beta V saturation present at the positive terminal will be higher, and if the voltage at the positive terminal is higher, the output gets transition to the positive V saturation. In this way, the output will be transited from plus or minus V saturation, and according to the output, the voltage across the capacitor will the capacitor will charge and discharge, and the voltage present at the positive terminal will also getting varied through the potential dividers, and whenever the voltage at the negative terminal exceeds the voltage at the positive terminal, or it crosses the positive terminal, the output will change from one state to other state. So, the two states of the output waveform are not stable because it is getting transited once because of the capacitor charging and discharging at the output voltage. So, both the states are unstable states in the case of astable multivibrator. Now, we have to derive the time period of the output voltage. Before that, we will see the output waveform and the capacitor waveform of astable multivibrator. So, this square waveform is the output of the astable multivibrator, and this waveform, the triangle like waveform, is the capacitor's voltage. So, for example, if the output voltage is considered as positive or positive V saturation, in this case instead of V out we can say this as V saturation, and if this is positive V saturation, the capacitor starts charging towards the positive V saturation, and once it attains the beta V saturation, then the output will be transited to minus V saturation. And in this case again the capacitor is discharging towards minus V saturation. Once it is discharging lesser than this minus V saturation, say it is minus beta V saturation, then the output will get transited to positive V saturation. So here this is actually, instead of V out, you can name this as V saturation and here as this term as beta V saturation. Here too this is minus beta V saturation and this is minus V saturation. Both are one and the same. V out and V saturation are one and the same, but because of the understanding of the concept, we are making it as V saturation instead of V out. So the capacitor is charging and discharging between minus beta and plus beta V saturation. The output is getting transited between plus V saturation and minus V saturation. This is the output waveform of the astable multivibrator. So this output has two states and no state has a stable is a stable one, because it gets transition due to the charging and discharging of the capacitor. And now we have to calculate the time period of the output waveform by calculating the voltage across the capacitor. The capacitor voltage Vc of t is given as Vf plus Vi minus Vf into e power minus t by Rc. Consider the final voltage. Vf is the final voltage, Vi is the initial voltage, Vc of t is the capacitor voltage from which we are going to calculate the time period of the output waveform. The final voltage is considered as V saturation plus V saturation, and so the initial voltage will be, when you look at the graph, if the final voltage is positive V saturation, then the capacitor's initial voltage is minus beta V saturation. If from minus beta V saturation, the capacitor starts charging towards the final value plus V saturation. So you have to consider this Vi, the initial voltage, as minus beta V saturation. Substitute these values in this equation Vc of t, which is equal to V saturation plus minus beta V saturation minus final value is V saturation into e power minus t by Rc. Here V saturation is taken out, plus V saturation is taken out, and you will have minus beta minus 1 e power minus t by Rc. This is your Vc of t. At small t is equal to capital T1, what is the value of the capacitor's voltage? So for this particular time period T1, the capacitor voltage is plus beta V saturation. So substitute Vc of t at t is equal to T1, Vc of t is plus beta V saturation. The equation will become beta V saturation is equal to V saturation. If you take this V saturation out, you will have 1 plus, okay, take this minus out. If you take minus out, you have minus 1 plus beta e power minus t by, instead of small t, you put it as capital T1. Now this V saturation will get cancelled. Beta minus 1, if you take this 1 to the left hand side, it is beta minus 1. You have other minus here, 1 plus beta e power minus T1 by RC. If you want to cancel out the exponential term, take natural logarithm. This equation now will become beta minus 1 by 1 plus beta. From this term is taken to the denominator in the left hand side. So you have a minus sign also here. So if you take this minus here, you have 1 minus beta, then e power minus T1 by RC. Now take natural logarithm. Minus T1 by RC is equal to natural logarithm. If you take natural logarithm, this exponential will get cancelled in the right hand side. So I have given directly T1 by RC is equal to, for this term if you take natural logarithm, it is 1 minus beta by 1 plus beta, and T1 is equal to RC natural logarithm, and this minus, if you put it here minus natural logarithm, then it will be this two terms will get reversed. So you have 1 plus beta in the numerator and 1 minus beta in the denominator. This is the time period for 1/2 of the output T1, and for the total time period it is 2 into RC natural logarithm. For total time period T, it is 2 RC natural logarithm of this whole portion 1 plus beta by 1 minus beta. For designing of the square wave astable multivibrator or astable multivibrator, you have to consider the value of R1 and R2 as R1 is equal to 1.16 R2. In that case, it is T is equal to 2 RC. If R1 is equally considered as R2, then T is equal to 2 RC natural logarithm of 3. So for designing, if you choose both the resistors equal, then the time period of the output waveform is 2 RC natural logarithm of 3, and if R1 is equal to 1.16 R2, then it is simply T is equal to 2 RC. So this is the time period, the total time period of the output waveform of a stable multivibrator. And what is the difference? This is also an unstable multivibrator, but there is a difference in the circuit diagram with the previous circuit diagram. This is a basic astable multivibrator, and here I have included 2 Zener diodes back to back. So if you want to change the output voltage, normally the output voltage of the stable multivibrator is plus or minus V saturation. If you want to reduce the output voltage, then these 2 Zener diodes are connected back to back, and at any point of time one of the Zener diode is in conduction and the other one is in reverse bias, it won't conduct. The output voltage in that case is Vz plus Vd. So Vz is the breakdown voltage and Vd is the forward voltage of the Zener diode, and peak to peak if you want to calculate, it is 2 into Vz plus Vd for the output voltage. So in order to have a lower value lesser than the saturated output voltage, then this is the setup of a stable multivibrator. So at that time the output voltage of the circuit will be Vz plus Vd. So the next is design of a stable multivibrator. The design is for the time period 1 millisecond. Just now we have calculated the time period of the stable multivibrator as T is equal to 2 RC if R1 is equal to 1.16 R2. The resistors, so now I have considered the resistances as this is R1, this is R2, the feedback factor is R2 by R1 plus R2. So for this resistors, take this as R, this as R, this as C. So for this name of the voltage divider and the RC network, I have derived the equation as T is equal to 2 RC if R1 is equal to 1.16 R2. So for the design, the time period is given as 1 millisecond. So T is given as 1 millisecond and it is 2 RC. This R and C is the RC network connected to the negative terminal of operational amplifier, and C you have to assume 0.1 microfarad. So from this equation calculate what is R and assume R1 as 10 kilo ohms. Calculate what is R2 from this equation, and now you have calculated the resistor values R1, R2, R and C for the time period T. So put all these passive components and construct an stable multivibrator, then you will definitely get the output waveform for the time period 1 millisecond, and this is the total time period. So for the full square wave or a rectangular wave, it is actually equally divided. So it is a square wave equally divided. So for the square wave, the full wave, the time period must be 1 millisecond if you note it down. So this is the design of the stable multivibrator circuit. If the resistors are R1 and if R1 is equal to R2, then beta is equal to R2 by R1 plus R2. In this case, T is equal to 2 RC natural logarithm of 3. So for this, if you calculate, then the time period must be equal to 2 RC. In that case, it is actually given as 1 millisecond. So you have to choose the resistors whether it is equal or it is 1.16 times R1 is equal to 1.16 times R2. We have to decide the values of R1 and R2, that is the feedback factor of the stable multivibrator. So in this session we have discussed the stable mode of operation of the multivibrator and the derivation of the output waveform, the frequency of the output waveform, and we have designed a stable multivibrator also. So from this, you tell me answer these questions, discuss the stable mode of operation of the multivibrator circuit, and there are two states of output, neither of which are stable. Whether is this true or not? Give the other name of the stable multivibrator. So I have given it as it is a free running oscillator, since it doesn't have a external input signal. There is no external input signal given to the circuit, so it is a free running oscillator. For an oscillator, we know that there is no input signal externally given, and because of the charging and discharging of the capacitor, the output will get transited from one state to the other state. So no states are stable. This is actually true. There are two states of the output, neither of which are stable. It is true. Because of the charging and discharging of the capacitor, no state is stable. And these are the references. Thank you.